A team I know spent 4 months building an AI assistant for their internal support function. The model quality was excellent. Output accuracy was above their target threshold. The engineering was clean. They shipped it to 200 internal users. 30 days later, adoption had dropped by 60%. Ticket volume through the old system, the slow manual one, that had actually gone up. Then the team ran a survey. The number one piece of feedback was not the answers were wrong. It was, it takes too long. The model was not too slow. The model was performing exactly as expected. So what was actually happening? Here is that team's architecture. And I want you to look at it because nothing here looks wrong. This is a completely standard, reasonable way to build an AI application. Request comes in, model generates a response, request gets written to a database, response goes back to the user. Clean, logical, sequential. Most teams build exactly this, but there are 7 decisions buried inside this diagram. Decisions that are invisible at prototype scale, that are each adding latency. Not because they are mistakes, but because they were made at a stage where latency was not a constraint and they were never revisited. At prototype, you have low traffic, warm connections, small prompts, and you are usually the one testing it yourself. So you wait. In production, none of these things are guaranteed and the decisions compound. This is what I call the latency stack. 7 layers, each one adding time, each one fixable, and together they are the reasons that teams' users went back to the manual system. Now I'm going to walk you through every layer, what causes it, how much it costs, exactly how to fix it, starting with the one that has the highest impact on how users actually experience your application. Look at the left side, then the right side. The same model, same prompt, total generation time is identical. But one of these feels broken and one of them feels like it works. Now, here's what is happening. When you call a language model and wait for the complete response before showing it to another user, you are forcing them to stare at a spinner for the entire duration of inference. In production, that is anywhere from 2 to 8 seconds depending on prompt length, model size, and what else is happening on that provider's infrastructure. Streaming changes the experience completely. You are not making the model faster. The total completion time is the same, but with streaming enabled, the first token arrives at the client in under a second. The interface feels alive. Think about how the ChatGPT responses streams when you interact with it. It feels like it is working, and that perpetual shift is enormous for user experience because users have been trained by major AI product to expect that first word almost immediately. And yet I see production AI applications without streaming constantly. Not because the team doesn't know about it, but because in prototype it did not feel necessary. The demo was fast enough, but it never got built. Both major model APIs support streaming. Most self-hosted inference servers support streaming. The implementation change is localized. It touches your API call and your response handler and nothing else. This is the first thing you fix, always. Now let's move on to the second layer. And this is the one that lives in almost every production code base I have ever reviewed. And when I point it out, the usual reaction is, oh, this is embarrassing. After the model responds, the server writes to the database, logging the session, storing the result, recording analytics. That's really important. Completely reasonable things to do. But the code awaits that write before returning the response to the user, which means the user is waiting for a database operations to complete that has zero effect on what they are about to see. The database write is not serving the user. It is serving you, your logs, your analytics, your audit trail. It should not be on the critical path of user experience. I call it fire and forget. Start the write to the database, but do not await it. Return the response to the user immediately. This is a small localized change, not a risky factor, and it recovers 200 to 500 milliseconds on every single request, and that's massive when it comes to user experience. At any meaningful scale, that is significant amount of collective user time given back. One important note: fire and forget means you need proper error handling on the async write path. You are not ignoring failures. You are just not making the users wait for them. Log errors, set up alerts, but do not let a database hiccup propagate into the user-facing latency. Moving on to the third layer. You see, most AI applications do not make a single call and return a response. They do several things. Call the model, write to the database, hit an external API for a tool call, update a cache, send an event to an analytics pipeline, and by default, all of these run one after another. But most of them are independent of each other. The database write does not depend on the external API call. The analytics event does not depend on the model response being confirmed by the database. When operations are independent, running them sequentially is purely a habit. It is not a requirement. Concurrent task groups, async parallel execution. The pattern is same regardless of your stack. Identify the operations that do not have a dependency on each other and run them together. On complex response flows with 3 or 4 background operations, this recovers 2 to 5 seconds. The key discipline here is mapping dependency graph before you write code, not after. Ask yourself and your team, what does each operation actually need to start? If the answer is not the result of the previous step, it should not be waiting for it. The next layer. This one is specific to a deployment pattern that has become the default of production AI applications. Serverless functions, Vercel, Lambda, Cloud Run. These platforms scale to 0 when there is no traffic, which sounds great for cost, but it means the first request after a period of inactivity has to wake the function up first. A cold start on a serverless function running an AI workload can add 500 milliseconds to 3 seconds before application logic even begins executing, before the model call, before anything. And in a low to medium traffic application, cold start happen frequently, not just on the first request of the day. And this does not show up in prototype because you are hitting the function constantly during development. It is always warm. It surfaces in production where movement traffic is uneven, which is almost always. The fixes depend on your platform. Most serverless providers let you configure a minimum number of warm instances. You pay a small, always on cost to eliminate cold starts entirely. Alternatively, a scheduled ping every few minutes keeps the function warm without changing your architecture. If your handler is lightweight enough, move it to an edge runtime, which starts dramatically faster than a full serverless function. The point is, if you are on serverless and have not thought about cold starts, you have a latency floor that none of the other optimizations can get you below. Fix the floor first. Now, most AI applications have a large static system prompt. Your instructions, your rubrics, your few short examples, your constraints, and brand guidelines. This prompt might be 2000 to 5000 tokens, and it is identical for every user. But by default, the model provider processes that entire prompt from scratch on every single request. Every user, every time, paying the full inference cost and the full time to token first penalty for content that never changes. Prompt caching, available through the major model APIs, lets you mark your system prompt as cacheable. Cache hits return with significantly lower time to first token. The cost reduction is substantial here, and you should take a note. Cache hits are dramatically cheaper per token than fresh inference. And because it applies to every request, the savings are not additive. They are multiplicative with your traffic. The implementation is a single parameter change on the API call. Now, the trade-off here is that the caches have a time to live, typically a few minutes. So very low traffic applications may not see cache hits constantly. But for any applications with moderate to average traffic and a large static prompt, this is not an optimization. It is table stakes. Now, this is subtle and it is almost never discussed. Time to first token. This is not fixed for a given model. It scales with the size of the input context. The more tokens you send, the longer the model takes to start responding. Now, teams building production AI applications tend to accumulate context over time. Conversation history gets appended in full. RAG pipelines retrieve 5 chunks when 2 would do. Tool call outputs get passed back in their entirety. Each addition feels justified individually. Together, they create an input that is 2 or 3 times larger than it needs to be. And at a time to first token penalty that compounds on every turn of a conversation. So you have to keep that in mind. The discipline is intentional context management. Not stripping everything, but being deliberate about what the model actually needs to generate the next response. Recent conversation turns matter more than the old ones. You have to adopt the habit of truncating on summarizing history beyond a window. You have to retrieve fewer, more relevant RAG chunks rather than more, less frequent ones. You have to pass only the fields from the tool outputs that the next step requires. That's it. A well-managed context window can reduce the time to first token by 30 to 50% on multi-turn conversations without any change to output quality. And that is massive. It is one of the highest return on investment optimizations available and one of the least commonly implemented. Trust me. Now, the last layer is about matching the model to the task, not defaulting to your best model every time. Most AI applications have at least 2 distinct types of work happening inside them. They are reasoning heavy tasks, structured, analysis, scoring, extraction, complex decision logic. These require your most capable model. And then there are generation tasks. Write a short conversational response, formatting output, summarizing a result that was already computed. These do not require a complex reasoning model. A smaller, faster model handles generation tasks 3 to 5 times more quickly than a complex model, at a fraction of the cost. The output quality difference on these tasks is negligible because the hard thinking was already done the step before by the complex model. So in short, you have to choose the right model for the right task. It sounds obvious when you say it, but the default in most production systems is one model for everything because it is simpler to manage and because the performance difference was not visible at prototype scale. In production, at volume, the latency difference is significant and the cost difference is substantial. Audit your pipeline. Identify which steps are reasoning and which are generation. Move the generation steps to a faster model. This is a localized change with a measurable payoff, and you should take a note of it. Now, when you put them all together in a performance optimization process for an AI application, here is the sequence I would follow. You can start with the streaming piece, the layer 1. Highest impact on perceived latency, lowest implementation risk. Then move the database writes off the critical path. Small change, immediate payoff. Then map your dependency graph and run independent operations in parallel. Before doing anything else, check your deployment for cold starts. If you are on serverless and not managing warm instances, you have a latency floor that undermines everything above it. So you have to take note of it. From there, implement prompt caching if you have a large static system prompt. Context window auditing if you are running multi-turn conversations or RAG, and model tiering if you have identifiable generation-only steps in your pipeline. One important note before I close. Everything I have described today applies to a conversational AI application with a relatively straightforward request-response architecture. If you are building a retrieval augmented system, and most production enterprise applications are, the retrieval pipeline itself is a separate latency stack. Vector search latency, embedding generation time, re-ranking passes, chunk size decisions. These are their own set of architectural choices with their own optimization sequence. That deserves its own video, and I will do it. But the 7 layers I have described today apply on top of whatever retrieval architecture you are running. The team I told you about at the start, the one with 60% adoption drop on their internal support chat assistant, they fixed 5 of these 7 layers over 2 weeks. No model changes, no infrastructure upgrades, no new vendor. Minimum change cost. The adoption was recovered. The manual system ticket volume dropped back down, and the engineers told me the most frustrating part was how obvious these fixes seemed in retrospect and how invisible they had been before. The model was never the problem. It almost never is. If you are shipping AI applications to production, treat latency as a first-class concern from the start, not an optimization problem you address after users complain. The stack I described today is not complicated, but it will not fix itself. Fast models do not ship fast applications. Thoughtful architecture does. If this has been useful, please subscribe to my YouTube channel. I publish production AI frameworks like this every week. Link is below. And if you're dealing with a specific latency problem in your production system right now, drop in comments. I read everything. Thank you very much for watching. See you next time. Bye.